Welcome back. Okay, the most important apart from the definition of probability, the most other important thing we're going to look at is the idea of independence. So independence is what we're going to exploit in a lot of the representations we build. So variable x is independent of random variable y given z if the probability of x given y and z is equal to the probability of x given z. Okay, so that's going to be what we're going to mean here. So we can add y in here, it doesn't change it. So what does that mean? Well, this means for all xi, for all yj, and for all yk, and for all zm, notice we have x equals xi in all the left-hand side of here. We're always talking about x equals xi, and we're always talking about conditioning on the fact we've observed a particular value of z. And what's important here is that these three things, so this one here says that if we have y is equal to yj, and then it's the same as having y is equal to yk. So it doesn't matter if we change the value of y, we're not going to change the conditional probability. And it's the same as not having anything about y. So we can interpret this as the knowledge of y's value doesn't affect the belief in the value of x given a value for z. So that's what we're going to mean by independence. So independence is a fundamental concept we're going to look at. So as an example, consider whether a student writing an exam, what are reasonable independencies amongst the following: where the student works hard, where the student is intelligent, the student's answers on the exam, or the student's mark on an exam. Well, it's reasonable to assume that W is independent of I. Independent of I. Okay, it's reasonable to assume that W is independent of I. Okay, it's also reasonable to depend on the marks is independent of the intelligence given the answers. So M is independent of whether they work hard or, given the answers. Okay. So the mark only depends on the answers. It doesn't depend on whether they work hard or whether they're intelligent. So also I, M is independent of I given A. So given the answers, we don't know whether they're intelligent or work hard. We only know their answers. Of course, their answers depend on whether they're intelligent or work hard, but these are reasonable independence assumptions that we're going to use in here. I'm going to exploit this for writing this domain. Okay, here's another domain. So here's a domain where we have outside power. We have power coming into the house, and we have circuit breakers, and power goes along these wires. And when we get to a switch, if it's down, if the switch 1 is down, then the power goes into wire W2. If the switch was up, it goes into power W1. Switch 2 either selects between whether we get power from W2 or W1. W0 is the wire here, and this depends on whether there's power in here depends on where the position of the switch is and whether there's something in the wire, and it's sort of independent, doesn't matter everything else. This is how we're going to exploit it, right? So whether L1 is lit only depends on whether there's power in W0. Okay, so that's what we're going to do. So whether L1 is lit only depends on whether there's power in W0. Whether there's power in W0 only depends on the position of the switches and whether there is power in either W1 or W2. Whether there's power in W2 only depends on whether there's power in this wire here and whether the switch is up or down. Okay, so this is the sort of information we're going to exploit in here. Okay, so let's write that down. So here's a few examples. The identity of the Queen of Canada. Think about whether it's dependent or independent of whether L1 is lit, given there is outside power. Well, it's sort of irrelevant to it, so it's independent. Whether someone in the room is independent of whether the light L1 is lit, given, well, how could someone, so think about what we're going to write here. Okay, given what? So whether there's someone in the room is independent of whether the L1 is lit. Well, how does someone affect the lit? Well, whether the light's on or not is certainly not independent of whether there's someone in the room, because they're very highly correlated. However, you would expect that it's given the position of the switch, it's independent of it. So the way the person's going to do it is the switch position. But if we knew the switch position, then whether they're in the room or not is irrelevant. Okay. Whether the light is lit might be independent of the switch position, given there's power. Okay. Every other variable may be independent of light is given there's power in this W0, whether there's light in W1. So whether this is lit, so let's go back here, whether this one is lit, whether this one is lit only depends on whether there's power in here and whether the light's broken or not. Everything else is independent. So that's this idea we're going to exploit here. So what we're going to do is we're going to build a network. So we're going to build these random variables here are going to correspond to nodes. And this we're going to say L1 is lit depends only on the status of light L1, which is this variable here, and whether there's power in W0. And they're going to then be the parents. So this L1 is lit, these arrows here going into it say depends on. So L1 is lit depends on that and is independent of everything else. So this one here is the parents of it. We go back and look at W0 depends only whether there's power in W1, whether there's power in W2, then the position of the switch and the status of the switch, whether it's broken or not. And that's what this W1. So they're going to be the parents. Okay, so that's what our graphical model is going to. That's the idea of a belief network. It's just this representation of conditional independence. So let's try and formalize that, what we just said. So what we're going to assume is we have a whole lot of variables of interest, x1 to xn, and we're going to put them in a total order. We're going to put them in a particular ordering. And it turns out the theorem of probability, this chain rule we did before, so the probability of x1 to xn is the product from I is 1 to n, of the probability of xi given the previous ones. This is just the chain rule. And now we've got to formalize this idea of the parents. So the parents of xi are those predecessors of xi, such predecessors of xi, that render x as independent of the other predecessors. Okay, so it's the parents of those predecessors of xi that render xi is independent of the other predecessors. So everything that predecessors is the ones that come before it in the ordering. So that's parents, that's the ones on the right-hand side are the predecessors of xi. So the parents are a subset of x1 to xi minus 1, such that the probability of x given the parents is equal to the probability of x given x1 to xi minus 1. Of course, in the worst case, we can just use x1 to the parents, could be just all of them, in which case we haven't made any assumptions at all, but often we're going to only depend on very few of the predecessors. Okay, and if we do that, it's pretty easy to see that the probability of x1 to xi is this product of probability of xi given the parents of xi. Okay, so it's a belief network. So a belief network is a graph. The nodes are random variables. So the nodes are random variables, and there's an arc from the parents of each node into that node. So that's what we're going to mean by a belief network. So here's the belief network for this. So L1 is lit. So L1 is lit. Here depends only on whether there's power in W0 and whether the status of it, whether it's broken or not. The power W0 only depends on the position of the switch. So switch S2 goes into it. The status of S1, W1, and W2. Okay, these in turn depend on the position of S1 and this other one, and the power W3. And W3 here just depends on how the circuit breakers works and whether there's outside power. Okay, so you can download this if you go to the AI space. We're going to give an example of that in a minute. So here's another example. So here's given a belief network for the variables in order of works hard, intelligent, answers, and marks. So first of all, we're going to write down Works hard has no parent, so we're just going to write down work. I'll just write works hard. Okay. Now we're going to have another variable which is called intelligence, and I'm going to assume that they're independent of each other. Now the answers, I'll just write here as A, depend on both of these. Okay, so there's no independence. So the A depends on whether they work hard and the intelligence, but the mark, however, if you knew the answers, that's all we're going to see. It just depends only on the answers. It's independent of whether they work hard or intelligent given the answers. So here's a belief network for that example. All right. Now you think about what happens if the variables were in the opposite order, and it turns out that you get a different network. So here's an example of what we did. So here's the story we're going to look at. So here's a story about whether there's a fire. There's a variables is whether there's a fire in the building. Whether someone's been, so that's the variable fire. All these are Boolean. Whether tampering is someone's been tampering with a fire alarm. Smoke, and says what appears to be smoke coming from an upstairs window. The alarm is whether the fire alarm goes on or off. Leaving is people are leaving the building en masse. And report is someone says, oh, lots of people are leaving the building en masse. So that's what is happening here. So maybe someone is in the other building and looks out the window and sees them. So what we're going to do is that this report is a noisy sensor for someone leaving. Okay. And so what we're going to do is we're going to look at this fire alarm belief network, and we're going to have a look at what's going on here. So let's look at this network. So here's the AI space network, and I'm going to load a sample problem. I'm going to look at the fire alarm belief network. I'm going to load that. Okay, and I'm in create mode here. And when I click on tampering, so I'm going to look at set properties. If you look at tampering, it's going to have the name is tampering and the domain is true and is TNF, true and false. Okay, similarly, alarm has domain true and false. We also have, as part of this network, so this is this independence assumption. So this says that the report only depends on leaving and is independent of other things. Leaving here only depends on the alarm. It's independent of whether there was tampering and fire. This says that the alarm depends on both tampering and fire, but smoke only depends on fire. So that's what this says. So each of these are Boolean variables, and they'll have a conditional probability table associated with it. So this has tampering has the probability of tampering, which I'm going to assume here is 0.02, which is 2%. The probability that there's no tampering then is 0.98. Fire here is this probability of fire is 0.01, and the probability there's no fire is 0.99. Something like smoke depends on fire, so there's going to have a different value of probability of smoke for the different values of fire. So assuming that if there is fire is true, then the probability of smoke is 0.9. If fire is false, the probability of smoke is 0.01. So smoke depends on fire, and this conditional probability table specifies how smoke depends on fire. And we have alarm. Now it depends on both tampering and fire, and then this conditional probability table here tells us how alarm depends on tampering and fire. For every value of tampering and fire, there can be a different probability. So here we're assuming that if there's been tampering and there is a fire, there's only a 50% chance of alarm. If there's tampering and no fire, there's an 85% chance of alarm. If there's no tampering and fire, there's a 0.99 chance of alarm. And if there's no tampering and no fire, then here we assume that there is no alarm. Okay, that's what we're going to specify in here. So while we're here, let's look at what's going on here. So if we can click on solve mode, and I'm going to look at what's called toggle monitoring, and then click on this node that says the probability of tampering is 0.02. The probability of fire is 0.01. Well, now we want the probability of smoke. Well, smoke depends on whether there's fire, and so we had that conditional probability. It turns out the probability of smoke is 0.02. The probability alarm here is 0.03. The probability of leaving is 0.02, and the probability of report is 0.03. Okay. And now now we can do conditioning. So what does conditioning do? Well, conditioning means that we're going to make an observation. So I click on make observation here. And if I observe smoke is true, then what happens is it's quite likely there's fire, and that makes alarm more likely and leaving more likely, report more likely. Okay, so that's what happens here. The probability of tampering did not change. Okay, so if I change this to none, then I'm assuming it's exactly the same as before. If I say there was a report, well, there's a chance there's tampering and there's a chance that there's fire. Okay, so there's maybe it's just tampering, and so it turns out here that tampering is more likely than fire. If, however, I also observe smoke, then it's much more likely that it's fire, and it's very unlikely that it's tampering. Right? The fact that so it's now very likely there's a fire, it's very likely there's an alarm, it's very likely there's leaving, and it's unlikely there's an alarm. If there was no smoke, if we observe no smoke, well, there's still only a 52% chance of tampering, and it could be the case that the report might be, there's still only a small chance that there's leaving, so not so convinced that there's leaving. Okay, so that's what we're going to do. This is the sort of network we're going to do, and all this is all we have here is this conditional independence table, this conditional independence assumption, and this assumption that says that the probability of leaving only depends on alarm. Okay, so that's what's going on here. So let's move this back over there. Okay, and now we're going to do this. So a belief network consists of a directed acyclic graph with nodes labeled with random variables, a domain for each random variable, and a set of conditional probabilities, one for each variable given its parents. And that includes the prior probability for the nodes with no parents. So nodes with no parents just have a prior probability in here. And so here's the network again for the electrical system. And so you also specify the domain of the variables, and here we've assumed that they're live and dead and up and down, and maybe that the status has these 5 different values. And then there's conditional probabilities of the probability of W1 given the position, whether it's okay, and whether it's live or whether it's dead. So we have these different conditional probabilities are specified. Okay, so a belief network is a directed acyclic graph where the nodes are random variables. The parents for node n are those variables on which n directly depends. The belief network is automatically acyclic by construction, and it's a graphical representation of dependence and independence. A variable is independent of its non-descendants, those variables that are not descendants of it, given its parents. So it's this structured way of having independence. Okay, we'll talk more about this in class. Thank you.